And what else should I mention? Deep
Game theory.
as well as game theory mechanism design. Okay?
Yeah.
So perhaps at some point we'll also get something related to that from you also.
Yeah, sure.
Regarding
Yeah.
you should sort of clue in some of the research questions.
Yes,
that
yes,
would be really nice.
yes.
Thank you.
Yeah.
So
Yeah. Thank you, Professor Anirban, and thanks to ACM for inviting me to give this talk. So I will be changing some of the things slightly. So so we will have the MLP, which is multi-layer perceptron or a feed-forward neural network. The discussion on that we will do first, and followed by clustering, and the last session for the after the lunch we will do decision trees, random forests, and so on. Okay, the purpose is I would like to like start with the math so that in the morning you are able to grasp it well. Okay, so yeah, so please do interact. There is a lot of audience over in the internet as well, so they will also have questions that you do. So if you have any questions, do feel free to interrupt. All right, so we will get started. So let's briefly talk about today's application area, which is feed forward neural network. Okay. So now what's the basic idea? So let's say we have a handwritten digit recognition problem, right? A very standard problem. All of you have seen it. Perhaps you have already used it in one of your lab assignments. I don't know. So what would you like to do? So basically you have an image of certain dimensions, let's say 28 cross 28, right? And within the image, you have these pixels, and the pixels indicate the handwritten digit, right? So something like a 1 or a 2 and so on, right? So let's say 1, you may have some digits where there is a 3 and so on, right? Now, typically, right? So how would one go about doing this? Like you would like to detect this, right? So you have been given a large data set of training samples with 1s and 2s and 3s and so on. You would like to be able to detect these digits, and the way you go about doing that is you perhaps one thing is you can directly take your features xi to be xi1 to all the way till xi 28 times 28, whatever that number is. You could take this as a feature, right? Or perhaps you might want to do something else. You may want to do feature engineering. So you would like to look at the image and try to detect some features about the image, right? So you may want to know if there is any. So the features could be xi1 could be are there any vertical lines? Okay, and xi2, for example, could be what are all the closed so are there any closed areas, right? So for example, for numbers such as if you have a 9, right? So if you have a 9 or if you have a 9 or 8, you will have these closed areas, right? So these kind of things you may want to feature engineer. Okay, so now the question arises, how do you know whether the way you are engineering the features, that's the good way or not, right? So that's one of the challenges. So, and perhaps from these letters, if someone tries to switch to some other data set where the letters are a little different from the English alphabet, if they use some other alphabet, let's say Hindi or Gujarati or so on, so then your feature engineering may not work well, right? So there is a problem there. So what people have done is they have thought of a way to like to get over this, and the idea is you use what is called as a feed forward neural network. Okay, and it's a very simple thing. So you will see as I explain. We will understand all these steps, all the important things that come in a feed forward neural network. You will also get to do the back propagation training and everything yourself. Okay, so that's the goal. So let's see. So what exactly is happening? So what you will do is, so your image that forms what is called as an input layer. So this will be your xi1 all the way till xi 28 cross 28, and all of these will then feed into some kind of a neuron. Typically we use a linear neuron first, which is so it has so you will have some weight vector here. So the output of this will be W transpose X, and then you will add a bias B. Okay, and then you may have some activation function. I will describe all of these things in detail. So perhaps a sigmoid activation function. Okay, so what is it that we are detecting here? It is not that we are detecting one or two directly. We may want to be detecting if there is a vertical line, if there is a horizontal line, like that. Okay, so this particular operation, the whole goal of that operation is to detect one type of feature. So likewise, as you can see, you have W1. You may also want another neuron like this. And you may want to use some other activation function, which is tan H. Okay, and then after this forms one layer, and then you can have multiple such layers. Okay, so at the end of multiple such layers, finally at the end, you will have what is called as the loss layer. So there you will have one loss for every digit. So something like here. So this will be, let's say, prediction whether it is 1 or not. Okay, so P1, P2, all the way till P0. P0 is the P0 is whether it's a 0 or not. And then you will compare it with the training data given to you, Y0, Y1 up to Y9. And finally, you will have an aggregate loss. Okay, so you will sum that up, and that is your loss. Okay, so let me again try to recap what is happening here. Okay, so you have the input image. The direct goal is to feature engineer and not to directly detect the final output. Okay, whereas in a logistic model, you were directly detecting it, right? At the end of the features, you just detect it. But here we are doing intermediate operations. So the input image goes through all of these computational layers, and finally, after several such layers, what you want to do is you want to compute what is the loss incurred by this architecture. Okay, so this is an example of a feed forward neural network. So now, what is the question? What are the challenges here? What do we need to do to start using such an algorithm? Sorry? How many layers? But before that? Yeah, go ahead. So are you saying that you need to decide what output should come at each of these neurons? Yes. Yeah, so but that training data has been given to you. You have a training data set with all the input images, which you have flattened into a single vector, and that is your xi1 to xi28 cross 28, right? That's just a, is there a confusion there? Yeah, so that is true. So but we are not doing xi1 xi2 like that, right? So let me just be very clear. So here, these are pixels. Okay. So input layer, you are directly feeding the pixels, pixel data. So what I was explaining over here in the box line is like conventional machine learning. Suppose you wanted to do it yourself for a particular problem. What you may want to do is you may want to do some feature engineering. Does that answer your question? Okay, so in the input layer you have the pixel data, and you pass it through all these operations, and you get, the idea is each layer will compute some important feature which you will finally use to predict. That's the idea. Okay, so we will go into each of these neurons in much detail. You will understand all of these things very clearly. But my question is, to start using some algorithm like this, what are the things that we need to know? The architecture is fine. So you learned logistic regression, right? They described the model to you. What was the next thing about after that? Okay, so here it's a multiple class classification problem. So what happens is, at the end of you will have P0, P1 to P10, P9. Okay, so that indicates whether it is 0 or not, 1 or not, like that. Okay, and then you will compare it with the loss y naught, the label, which is whether that particular ith sample, whether it is 0 or not. So if you agree, then the loss will be less. If you disagree, the loss will be more. Okay, so usual logistic loss we can assume that we are doing here right now. Okay, so it's a classification problem, but it can be changed to regression problem as well. If the final here we change it to least mean square loss. Okay, so it can be done. So any other issue? Sorry. Yeah, so how do you, yeah, so that's correct, right? So what is the algorithm? How do you learn all these parameters? That's the goal, right? So what you have seen so many learning algorithms till now. So what is the usual technique that people use to learn these weights? Gradient descent. Yes, so that is what we will do. Okay, so first so there are two aspects of this feed forward neural network. First one is forward pass. Okay, so we will spend some time on the forward pass, and then second is back propagation. Okay, so these two things we will do, but before that we will have to spend some time to understand a few calculus preliminaries. Okay, so I will assume like it's a good thing to do. Perhaps all of you are already familiar, so it might, for next 5-10 minutes we will just do some recap. Okay, so first about lines. Okay, so we have to understand what is a hyperplane, right? So that's the first thing. Okay, so in 2-dimension, what is a line? You have learned analytical geometry in your +2, right? So what's that? Yeah, y is equal to mx plus c, right? So what that is essentially means, you have some intercept c, and this is your line. The slope of this line, so this is delta y delta x, the slope is m. Okay, so this is a usual line in 1D. Okay, so now the goal is to extend the line in higher dimensions. So how do you understand lines in higher dimension? All right, so the way one thinks about this is through vectors. Okay, and again, vectors you have already studied, you have seen it in the past. So vectors have what are the two things about vectors? Direction and magnitude. Okay, so if there are two vectors of the same length, pointing in the same direction, we know that they are the same vector, right? So they are identical vectors. Now, how does vectors, so this is vectors that you have studied in physics, right? So you have also, for example, studied if you take two vectors and if you do the parallelogram law, you can add it like this. Or if you take vectors and the head to tail, that also you can add it, right? So these things you have studied. You know how to add vectors, subtract vectors, and so on. So these are the things that you have learned in school in physics already. Okay. So now, so vectors in R2, for example, with if you put a coordinate system, what you have is this. So you will represent, there will be an origin, and if there's a vector like this, so you will tell what is the x coordinate, x1 coordinate, and what is the x2 coordinate. So for example, this is could be 1 1 1. Okay. And now you can check that if you add two vectors. So if I take let's say 0 1, and if I add, so this is x-axis is 1 1 0 and 0 1, right? If I add them, I will get 1 1. So all the usual parallelogram law, everything it obeys. Okay. Now all these things you would have seen at some point. So what is that got to do with the lines? So it's as follows. Okay. So let's say you have a line which is passing through the origin. So as one of you told, C is 0 for this line, right? Y is equal to mx plus C is 0. But instead of using the usual notion, what I will say instead is that this line, okay, all the vectors that lie in this line. So this is a vector in this line. This is another vector in this line. This is another vector in this line. All these vectors are orthogonal to another vector W. Okay, so this W is let's say W1, W2. Okay, so what is the meaning of orthogonal? If I say a vector is orthogonal to a line or a plane, so what does that mean? Sorry, it's normal to the plane, right? So what is the advantage? So in a two-dimensional, if it's a line, if this is a line, if I tell you the orthogonal vector, I can define the line. That's one. Also, okay, I was just looking for some flat surface, but yeah, okay. So if this is a plane, right, and I can define an orthogonal to the plane, I can define a plane. Do you see? So it has the added benefit of being generalizable to higher dimensions. Okay. So but what is the, how do you characterize two vectors being orthogonal? Their dot product is 0. Everybody is familiar with this, right? So what is the dot product between W and X? So how do you say? Sorry? Yeah, so she's saying that dot product is equal to W1 X1 plus W2 X2. Any other definitions that you know of dot product? Yeah. Yeah. So if there are two vectors, let's say W and X, and if the angle between them is theta, you can also define the dot product as W X cos theta. Okay. So these are the two equivalent definitions. Now, does anyone know why these two are, why it's true? It's a very interesting exercise. Okay, so this is something that you can try. So why is this true? Why is W1 X1 plus W2 X2 same as modulus of W times length of W, sorry, not modulus of W, length of W times length of x times cos theta. Okay, so you can figure this out. You spend some time and do it. It's an interesting exercise. Okay, so I will just say, okay, so you can do it. Just try it. Now, if two vectors are orthogonal, what is the cos theta of that between the two vectors? 90. Cos theta is, angle is 90, cos 90 is 0. Okay, so therefore, we have now got a representation for all the vectors in this line, which is all the vectors x. If x is a vector, in this line, we know that W transpose x is equal to 0. Okay, so this is what you typically define. So this is only for R2, but this generalizes to R3. In R3, W transpose, I gave you an example, right? Take a plane, take an orthogonal vector. Okay, so all the vectors that are orthogonal to this W, that forms a plane. Okay, so now unfortunately, from all the discussion that we have is only for W transpose x equal to 0. So we should be able to tell what if the line doesn't pass through the origin. Okay, so for that, it's a very simple exercise. I will just do it right away. So let's suppose that you have a W. Oh, sorry. So let's take a line passing through the origin like this. So this has the property that W transpose x, this is your W. So this is W transpose x equal to 0. Okay. Now let's take a parallel line. Okay. And the goal of our entire discussion for this is we want to find out, suppose if I take a vector on this line. So this is a vector x on the second line, the one which doesn't pass through the origin. I want to know what property that does that satisfy. Is that clear? Is the goal clear? Okay. So how does one go about it? So what you will do is first thing is you need to have a single point in the parallel line. Okay, so let's say this is a point. This point is some p. Okay, so what's the property of p? P is a point on the line. Okay, and what can I have a question here for all of you. W transpose p, what's the numerical value? Okay, so I will give you 3 choices. Don't start answering. I want to see how many of you really understand this. Okay, so how many of you think it's A? Can you raise your hands? How many of you think it's A? W transpose P is equal to 0. How many of you think it's A? What about B? Okay, 1, 2, 3, 4. Please raise your hands a little high. Okay, 4. And W transpose P is less than 0. Okay, so what about others? See, what is the angle between W and P? Sorry? Yeah, but P is not orthogonal to W, right? P does not lie in the line W transpose x equal to 0. P is a line which lies on the parallel. It lies on the parallel line, no? Correct? So W transpose P is not 0. At least I hope everybody understands that. Correct? So what about W transpose? What's the angle between W and P? Is it acute or obtuse? Acute. So it's a positive number. Okay. So W transpose P is a positive number, or it's actually positive but not 0. It's a non-negative number. It's a number strictly bigger than 0. Does everybody understand this? Okay. So now, what is the? It still doesn't answer the question that we are looking for. But let me just get back to that. So what we can say is that W1 P1 plus W2 P2. Suppose that is equal to a value B. That B is going to be greater than 0. Okay. Yes. Okay. So now, so how does that help us answer the equation of the line question that we were asking? Is as follows. My claim is you can decompose X. You can decompose. Okay. So you can decompose a X into P plus X minus P, right? I mean, that's just a simple adding and subtracting. But X minus P, if you visualize that, this is this vector, correct? Now, coming to your, you were saying, right? So what is the X minus P? Is it orthogonal to W or not? Yes, right? Because that's the same vector as this vector. So this vector is same as this vector. Remember? So therefore, W transpose X is equal to W transpose P plus W transpose X minus P. Okay. So now W transpose X, this is nothing but B. This other one is 0. Okay. So you have got equation of line W transpose X equal to B. So do you understand this? So that's about it, right? So so now in R2 we know what to do. W transpose X equal to B. So that's a line like this. This is your W. This is W transpose X equal to B. So now if you take any vector on the other side, so if I take a vector like this, okay, so suppose this vector is some Q. So W transpose Q, okay, is it greater than B? So again, the question ABC. Is it, so this is equal. So my question is, what is the relation here? Is it equal to 0, or is it sorry, is it equal to B, or is it less than B, or is it greater than B? So let's check. So how many of you think it is equal to B? What about less than B? Greater than B? Okay, so many more are raising the hands. Okay, so that's essentially correct. So because W transpose Q can be broken down into a vector over here plus this vector, right? And this is your W. So then same idea continues. W transpose that remainder vector. So this vector over here, this is greater than 0, whereas this vector W transpose with that vector is equal to B, right? So B plus something greater than B. So this is the idea of half spaces, right? So when you have a hyperplane, you have something greater than B on one side, less than B on one side. On the line, you have equal to B. Okay. All right. So this is about geometry of lines. Anybody has any questions? It's okay. All right. So now coming to a little bit of calculus. So now I would like to first define derivatives. Okay. So we will start with so the objective in next few minutes is derivatives in R1. Okay, so what does that mean? So if there is a function from R to R, what is the derivative? That's goal number 1. Okay, then derivatives for functions of the form f is a function from Rn to R. Okay, so what is the derivative for this case? And then we will also look at what is the derivative for the case where f is a function from Rn to Rm. Okay, so this is first is to study what are the derivatives. How do you take, how do you do differentiation for these types of functions? Okay, and the second is, after this we will look at chain rule. Okay, so this is one. Second one is chain rule. Okay, so now derivatives in R1, everybody has done it. So what is it? Somebody from this side? How do you define derivatives in R, like functions for R to R? I just hope you are shy and not answering, but right. So what anyone? Sorry. It's basically you look at the function, you plot the function, and then at any point you look at what is the tangent to that and the slope of that function at that point. That's the derivative, right? So so basically if you recollect, f dash x is defined as limit h tending to 0 f of x plus h minus f of x by h. Okay, so wherever this goes to, that is the derivative. This is, you have seen in your class 12th or class 11th or sometime, right? So this is the derivative in R1. Okay, so for derivatives in Rn, this for the second type Rn to R, we'll have to do some work, and let me show how that comes. Okay, so all of you have seen Taylor series expansion, right? So can you say what it is? So if I want to tell what is the expansion at f of x plus h, so how do you define it? So it's essentially this. So you have f of x plus h times f dash x plus h square f double dash x by 2 factorial, right? This is the Taylor series expansion in terms of at a point near x, in terms of all the derivatives at x. Okay, so you can rewrite this as f of x plus h of f dash x plus small o of h. Okay, so what is small o? So you have, how many of you are from CS background? Okay, many, almost all perhaps. So what is the small o or a big O? It's, sorry? Yeah, in time complex it is defined, but okay, so yeah, it is telling you, it's telling you basically rate of growth of your algorithm, right? How quickly is it growing, isn't it? So the same idea is extended in math also into the small o notation. It just means that this function goes to 0 very quickly. So that's essentially the meaning. Okay, it goes to 0 very quickly. So this basically it means it goes to 0 very quickly, and that means just the limit of this is 0. Okay, so that's essentially the meaning. But what h tends to 0, sorry. But whatever you said about growth of function is correct. So you are trying to do that, right? You want to upper bound your algorithm's complexity in certain way, isn't it? So using this, we are able to get an alternate definition of f dash x as follows. So basically what we get is, using this, we can write f dash x is defined as, so limit h tends to 0 f of x plus h minus f of x minus h of f dash x by h. Okay, this is equal to 0. So any function that satisfies this condition, any function that satisfies this condition is also a derivative. So that is another way of defining. Okay, so why all this story is because now we are ready to define derivatives for functions which are from Rn to R as follows, which is limit h tending to 0 okay. So any function t, okay, t is a function from, so by the way, when you took a derivative f dash, okay, the idea was you are approximating a function by a line, correct? So I took the slope and I took the tangent. So around the point x, it's a line that is the closest to that point, right? So you're approximating f as a line. Okay, so the same idea holds here. So t is it's almost like a line from Rn to R. It approximates linear approximation to the function f. It's a linear approximation. So any function that satisfies this. Now my question is for all of you, why have I put a double line for h and a single line for numerator? Upper one is absolute value. You can take an absolute value because f goes from Rn to R. So it's a single number in R. So you can take the absolute value. Whereas for the bottom one, it is magnitude. So you have to take the R2 norm or something like that. So you can have the 2 norm or something. Okay. So, so can you give me an example, a linear function? So I want to understand, I want to explain this a little more. So linear functions, I want an example of a linear function from Rn to R. So can you give me an example for a linear function? Yeah. So Rn is, so for example, right, in your image classification for the pixels, there were 28 cross 28, right? So if you consider it as a vector, each component is independent, correct? So that will first one will be R1, second one will the second R2, R3 like that. So n could be any number like that. Is that okay? So function from Rn to R. So something, suppose for example, if I'm adding all the pixels, right? So that takes from Rn to R. Do you see that? So I am trying to define the derivatives in this higher dimension. From Rn to R, there is a function. So can you approximate it as a line? That's the idea. Okay. So can you give me an example of a function from Rn to R? Huh? X transpose into X, right? So X transpose into X is not linear, but some other number, W transpose X. X transpose X is not linear. So what is linear, first of all? So if T is linear, it should satisfy this property. T of A plus B is equal to TA plus TB. And T of some 2 times A, for example, should be 2 times TA. Okay, so your example of X transpose X doesn't satisfy this. You can check it. Okay, so what does satisfy is example. So T of let's say some vector X is W transpose X. Okay, so this satisfies that. You can check it. These two properties it satisfies. Okay, so all right. So this is for Rn to R. Now for functions f from Rn to Rm, the definition is as follows. Sorry. Okay, first question again. Why did I write a double line here in the numerator as well this time? Yeah, so it's in RM vector. So you have to take, you cannot take the absolute value of a vector. Okay, so that's why we are taking the norm, the length of that vector. Okay, so now can you give me an example of a function which is linear from Rn to Rm? So linear, let me remind you, satisfies this property. So can you give me an example for a function from Rn to Rm? See, why so matrix multiplication, why was it defined like that? Right, that's I mean, because it is a function from Rn to Rm. So if you take a matrix of dimension, let's say 2 3 4 1 7 6. Okay, so now which vector can I multiply it with? Can I multiply it with a 2 cross 2 vector? Sorry, 2 cross 1 vector. I'm asking this times let's say 3 2. Is it possible? Can I do this? Huh? No. So this is not possible, right? So this is not possible. Whereas I can multiply it with the 3 2 1, right? So what it is doing? So this function example here is a function from R3 to R2. Okay. So matrix multiplication is a function from R3 to R2. Okay. Yes. For this example, it is R3 to R2, but depending upon the dimensions of your matrix, it's an appropriate function. Okay. So why all this story is because we need to understand how to take derivatives, because we want to do neural networks. Okay. So there is one thing, right? You can always use all these Keras, TensorFlow, whatever you want. There are already packages ready-made for you to use. But if you don't understand the internals, perhaps you may not be able to do something clever, even if it's right in front of you. So we need to understand this. So there is some effort involved. Okay. So, all right. So coming back to Rn to R, you have already studied this, but what's the derivative from Rn to R? I'm saying that you have already seen an example of this. In your logistic regression, you have already seen an example of this. Is it in logistic regression? Yeah. So if you look at the loss function, right? So if you had a you have done logistic regression already, right? So you were supposed to learn a WD vector. Okay. So you had a loss function which takes from WD to a number in R, and you were minimizing it. Right? And you used gradient descent. Gradient is nothing but, I mean, so you used gradient descent. So you already seen how to take the derivative for this. So what is that? Partial derivatives. Okay. So the derivative TF is basically a collection of partial derivatives df by dx1, df by dx2. Okay. So this is that. Okay. And then for a function g from Rn to Rm, we can, so when there is a function from Rn to Rm, you can think of it as m different functions G1 to Gm. Okay, you can think of that G as being equal to this, right? G1 to Gm, and so Tg is therefore G1 x1 del G2 x2 Gn xn, sorry, G1 x2 G1 xn. Okay, then G2 x1 G2 x2 okay. So this is how you can think of this. All right. So now yeah, so this is about the derivatives, and the second thing before we can really start is the chain rule. So can someone tell me what's the chain rule of calculus? In R1 to R1, right? What's the chain rule? What does the chain rule try to do? So let me ask you this way: what is d by dx of cos x squared? Sorry. So somebody said sin x squared into 2x, right? So why did we do this way? Sorry. Yeah, so this is the chain rule. So you take the outer function's derivative, then take the inner function. You keep going till you don't have anything left, right? So the idea is this. So you have a function f which goes from R1 to R1. Then you have a function g which goes from R1 to R1. You can define an h which is f of g of x, right? And if you take the derivative of h, this is same as okay. Do you remember this? And the analogous thing for if there is a function from Rn to Rm, is there echo? Maybe, yeah. I don't remember what exactly is. Perhaps it is there. I am not too sure. Yeah, if it is there, it is there. If it's not there, it's not there. I mean, I don't remember. But the point is, what I'm trying to say is this, right? So you have Rn to Rm, then there is a G, which is let's say Rm to Rk. So you can define f of x, and this will be a vector in Rm. Now you can apply G on it. Okay. Is this doable? So f of x is what? It's a vector in Rm, and you can apply G to it. It will become a vector in Rk, right? So so Tg should be a vector of what dimension? I was explaining you, right? So what is the dimensionality of Tg? Sorry about this. So there is a h. So h you can define as this. So yeah. So what is dimensionality of th, the vector th? So it is, see, you are trying to approximate h. Okay. H is a function from Rn to Rk, right? Yes. So this vector is a k cross n vector. Okay, so this you can decompose it as Tg times Tf. Tg is a vector from k cross m, and Tf is a vector from m cross n. So when you multiply two matrices of this dimension, k cross m and m cross n, you will actually get k cross n. Okay. Yes, so far everything is okay. Yes or no? Okay, so now we are actually in a position to start talking about back propagation. All right, so that's what we will do. But I just want to know if you have any questions. So there are two things we discussed: derivatives in higher dimension, and then chain rule. Okay, yeah. At matrices, so you can multiply them, right? So I gave you an example over here, right? So when you take the gradient, see, when I took the gradient TF, right? It's a vector. So this is a vector of 1 cross n. So this is a function from Rn to R. That's the way to understand the derivatives. Is that okay? So this, when you take df by dx1, it's a number. So that's the way to visualize this.
There is a question from online audience.
Yeah.
That, why bias is taken and what it actually does.
What?
What it actually does. Like
Which one?
Bias. The previous slide. Previously you were talking about the neurons, right? Like so inside that the bias is adding, right?
Oh yeah. Okay. So okay, there is a question. Let me just recap for everybody's benefit. So we began this entire discussion all the way back to this. Okay, it's a good question, so that we are back to what we started with. So we had this W transpose X plus some bias. So what does the bias B1 to B2 and so on, what does it add? It's just a simple thing. If you don't have W transpose X equal to B, you are restricting all the lines that are passing through origin. Whereas when you have a B, you are having a richer class, which is lines which need not necessarily all pass through the origin. So that's essentially the answer for that. Okay. All right. So far so good. Everything is hopefully clear. So let's look at a simple neural network. Okay, and let's try to analyze the forward pass and backward pass. All the discussion about the calculus was just so that you are not lost now, but perhaps you are already lost. But try to see if it makes sense, then it's okay. So let's take a simple example of a simple neural network. Okay, so this neural network has a very simple operation, which is, so this first operation, I will write it this way. So it has X and it has W. So the output is W transpose X. So then like it multiplies X and W, that's all. Okay, and then there is, so this operation, let me call it as some lambda, and then there is a alpha which adds a bias B. Okay, so this is a simple neural network. And what is X? So let me write what is X. So X is X11, X12, X1D. Okay, so this is your X. And what is W? W is a vector that you can multiply with this simple vector, which you can multiply. So let's take this as W11, W21, W. What should be the thing here? If I have to multiply XW,
WD1, WD1.
WD1. Okay. So this is the XW is, you can multiply. Let's say when you multiply, you will get a vector N. Okay, so when I multiply XW, I will call that as N1. So up to, what is this dimension?
NN.
Yeah. Okay. And so what does the bias term B do? So if I call this as a prediction P, so P is equal to what? N1 plus B, right?
Yeah.
N2 plus B.
Yeah.
Okay, and we are not yet done. We need to have a loss layer. So let's highlight the loss layer in a different color. So the loss layer takes the label y and it generates a loss which is equal to summation yi minus pi squared. Okay. So what is the forward pass? How does data propagate in this? Yes, how does the data propagate in this? What does the first blob do? It just multiplies w and x, correct? And you will get vectors n1 to nn. Okay. And what does the second blob do? It adds a bias b, same b to all of them. Okay. And that will give you predictions p1 to pn, and you compare that with y, which is your training data, you will get the loss. So is the forward pass clear? Yeah. So forward pass just takes, so what forward pass has is either it has some parameter or it does not have a parameter. If it has a parameter, it will just operate with that parameter, pass it to the next layer, next neuron. The next neuron will take that, do some operation, pass it to the next, and finally the loss is computed at the end. Okay. Yes. So now forward pass, I hope, is okay. By the way, what is this operation doing exactly? What does it remind you of? Linear regression. So this is a linear regression. Okay. So its linear regression can be thought of as a simple neural network. Okay. So this is linear regression. So if you all right. So forward pass I'm hoping this is clear. So now to do back propagation, the goal is very clear. We want to do gradient descent, right? So can somebody tell me what is the gradient descent? How do you do gradient descent? You have seen already, you have implemented also, I guess. So what is how do you do gradient descent to optimize the parameters? Yes. So you have some weights, the new weights, correct? You compute it from your old weights, add some kind of a learning rate. So because you are doing gradient descent, you want to reduce the loss, right? So this will be a negative, and then you will look at gradient of your loss with respect to w, right? So this is the gradient descent step. You have already done this, I presume, right? So this is what you need to do. You do this till you are reaching some convergence. Okay, once you reach convergence, that's it. So you stop and you report that as your learned model. Okay. So now here, if I have to do gradient descent, what do I need to do? So which are all the parameters that I am learning? Am I learning y? That's given to us, right? Am I learning x? Okay, so we will come back to x. What about w and b? Those are the parameters we need to do. So what we need to do is I need to tell you a way on how to do dl by db and dl by dw. These two things has to be clear for you, not just for this architecture, but even if there are multiple neurons. Okay, if I connect several things, so I could have here another complicated example. Another complicated example could be, you can have x here, your w is like this, but okay, but w is actually w11, w21, w22, w21, w12, w22, w2 31, 32. I could have something like this, right? So this, assuming that you go all the way till wd1, okay, and this is wd2. So what does this w do? if I have, instead of a single vector, if I had something like this, when I multiply, what do I get? What do I get? See, if I multiply by a vector, I will get n1 to nn, right? If I multiply with a matrix like this, I will get two different outputs, n1 and n2. So this is like your example that we started off with, isn't it? So where you want to detect a vertical line, you want to do something else, there were different operations, no? So these are like multiple operations are done in that box. Okay, so you can have something like this, then you can have a bias. So now how many bias terms will I be adding? 2. Okay, so B1, B2. And then the output of this can go to one more such layer. Okay, this can be your X, new X. There can be a W here. Okay, and I can keep on doing this. Okay, and I should be able to tell you how to do DL by DW for every stage. Otherwise, you won't be able to do back propagation. Sorry, you won't be able to do gradient descent. All right. Which one? B. B is, you understand what is W transpose X equal to 0, right? That's a line passing through the origin, or a hyperplane passing through the origin, correct? But when you add a allow for a B, you can have any line, need not necessarily be passing through origin. It can shift. Yeah, once you add the bias, it can shift. It's just an extra parameter. Okay, so my point is, even though we are looking at this simple example with a neural network, which is actually linear regression, the procedure that I'm going to describe should hopefully allow you to do any neural networks implementation after this. Okay, so that's why we will do this properly in detail, so that you have full tools necessary for doing this. Okay, so coming back to the original example, so let's look at one layer at the time from the back. So the last layer was the loss, right? So you had predictions, PIs, you had YIs, and there was a loss which was YI minus PI squared, right? So there are other things are there. I'm going to skip for now, but we will come to that when we come to that. We'll slowly try to see how it is done. See, when you do the forward pass, you do an operation, pass it to the next layer, you do some operation, pass it to the next layer, and so on, right? For the gradient part, you will see that you will do an operation at the end and then pass it back. Okay, so why is it like that? Because of chain rule, right? See, so if you have f of g of x, right? So if you think of it as forward pass, it is going from g to f, correct? But the gradient of this is what? F dash g of x times g dash x, right? So this is now going first f dash, then g dash. So it's reversing the operation. Okay, so that's why I spent so much time explaining chain rule. Okay, so let's anyway, if you don't understand this now, you will understand once we do a few more steps. So I now need to do loss. So I need to compute gradient for this. So loss is equal to yi minus pi squared. Okay, so this loss is a function from Rn to R. So what is the Rn I am talking about? Is it yi or is it pi? It is pi because yi is fixed. Okay, so what is the gradient L with respect to p? So what's the partial derivative of L with respect to p? Everything is there on the board.
The minus 2 times yi minus pi.
Okay, that's right. So this is equal to 2 times yi minus pi times minus pi. Okay. So it is 2 times yi minus pi into -1.
Del.
Okay. All right. So if I want to write it as a if I want to write it as a vector, I can write it as a row vector of this form: 2 times p1 minus y1, 2 times p2 minus y2. Does everybody understand this? Why is it this vector? Because again, the whole discussion on how to take gradients. Okay. So this is the gradient that is passed back. So the gradient that is passed back is a vector dl by dp1, dl by dp2, dl by dpn. So this is what is passed back to the next layer. Okay. So next, so this was the layer that we already saw. We will not worry about this anymore. This is your pi, this is your L, and this is yi. Now let us look at the previous layer, which is alpha and b, and then input is ni. Okay, and it adds, you know what it does. So pi is equal to ni plus b, right? The bias. See, I'm coming one by one step back. Okay. So now, so the goal is I need to be able to do dl by dni and dl by db. So dl by db, everyone knows why we need to do, but why dl by dni? Because ni is coming from the previous layer, which depends on the weights. So in order to compute the gradient for w, I need this intermediate step. Does everybody understand this? So why dl by dni is necessary? Did you follow? dl by dni, why is it necessary? Is it clear? Okay. Someone had a question. Okay. So what is dl by db? Okay. So this is where I want you to pay extra attention. So if I change b, what are all the values it will change? If I change b, so output of alpha is p1 to pn, right? If I change b, which of the p's it will change? Huh? So output of alpha is ni plus b, right? It's a vector. Ni plus n1 plus b, n2 plus b, like that, all the way till nn plus b. Okay, each n in n1 plus b is p1, n2 plus b is p2, like that. So my question is, if I change b, which of the p's it will change? All of them. And if p changes, does the loss change or not? Okay, so basically this is the idea. So I want to know if I change, if I change, so I will do at this, I will see which of the p's change and this. So this summation over I going from 1 to n. Do you understand this? So the first term is telling, if I change b, what is the change that is seen in pi? Okay, and then I'm seeing how much is the loss changing when pi is changing. So how do I know this first one? I just calculated from the previous stage. It is the input to this stage, right? So can you all tell me what is this equal to? What is dpi by b? Look at that expression and tell me. 1, right? So this is going to be okay. So what is this operation? Summation. If I sum it over, how do I do it? It is just taking the previous gradient and doing transpose 1. Okay, so it's like, if you want to do, this is dl by dp times 1. So that's exactly like summing it up. Okay, so you can now see how you can implement this in Python. Okay, so this is going to be one of your lab assignments to do this in Python, the way I am describing. Okay, so anyway, so is it clear, this step? No. Did you understand till here? Summation I equal to 1 to n this. Did you understand this? So what is this? This is inner product between dl by dp and ones, series of ones. There are 1, 1, 1, 1. If you take inner product, it just sums it up, right?
Yes, sir.
If you don't like this, let's say np dot sum dl by dp. Is that okay? That's what you are getting, right? Okay. So now this is for dl by db. What about dl by dni? So if I change the ith ni, if I change the ith input here, which output does it change? If I change the ith input, which output it changes? Sorry. So ni, I'm changing little bit. So output is P1 to Pn. Which one it changes, I'm saying? Only Pi.
Only
nothing
P.
else.
Yeah.
Yeah. So that means this will be dl by dpi times dpi by dni. So what is this? It's nothing but dl by dpi.
DL by DPI.
Yeah. Okay. So this operation is just taking whatever is coming from the previous layer and passing it down without any change. Okay. So this was the second output. So you have this yi. This is your alpha, right? Now you have bi. All these things we have seen. Here you are getting ni, and now we have this. This is the last thing that we need to do. You have x and you have w. Okay, so somehow what is the here? What you are getting is dl by dn. So here you are getting dl by dn. Here you are getting dl by dp. Okay, so now somehow I should show you how to do dl by dw and dl by dx. dl by dw, everybody knows why we need to do. Dl by dx, why should I do that? Why is dl by dx necessary? See, x is a part of your training data, right? Why should I look at the derivative with respect to x? Because it could be a part of many more layers. If it's part of many more layers, this dl by dx will be passed downstream for computations. Do you understand? Just the very same way why we needed dl by dn. Okay, so let's now try to do this. Okay. So we will focus only on one of these. So you have x, you have w, the output is ni. Okay, so just so that you know, I will just look at a little more complicated example than just w. So let's recall what is x. X is x11, x12, x1d, x21, x22, x2d, xn1, so w, I will just make it a little more complicated than before. This is what we originally had, right? wd w, sorry, what am I writing? Sorry about that. So w, we had w11, w21, w31, all the way till wd1. I will add one more row just so that you know there is a reason why I'm doing this. You will see w12, w22, wd2. Okay, so in the linear regression there was only one vector. I have just added one more vector just so that we get some for some reason you will soon see. the output will be Ni will be N11, N12, N21, N22, ND1, and D2. Okay, so I need to compute dl by dw and dl by dx. So this is the goal, right? We need to compute this. Okay, so let's get started. So dl by dx, dl by dw. Okay, so so w, how many parameters w are there? You have it here. So how many are there? 2D parameters are there, correct? So this is, if you want to think of loss function, if you just forget about everything else, it's a function from R2D to R. At this stage, if you forget about the rest of the things, it's just a function from R2D to R. Okay, so the gradient of L will be what? Gradient of L with respect to Wij, right? If you consider all the ij's, you can think of it as a matrix of the same dimension as W. Okay, so the goal is to compute dl by dw11, dl by dw12, dl by dw21. So this has the same shape as W, as the W vector. Okay, yes, so as the W parameter that we wanted. Okay, so now coming to the original problem over here, you are doing the matrix multiplication. So if I change W11, okay, if I change W11, which of the parameters will it change? Sorry. So you tell me in terms of N1, N11, N12, which of it will it change? I'm changing only W11.
N11.
Huh?
N11.
N1. I have only N11, N12, and so on. There is no N1.
Yes, sir.
The first row, first column. Yeah. So it will change all of these columns. Okay. Yeah. So essentially, so I'm changing W11 and I'll end up changing all of these columns. So dl by dw11, okay, it will be dl by n11 times Does everybody understand this? Uh, 1n w11. Okay, is this clear? You seem to be confused. Is it okay? See, when I change w11, right? So if I change w11, see, the first element n11 is matrix multiplication x11 w11 plus x12 w12, right? This into this into this, right? So the first one gets changed because of that. Okay, so what is dn1 time dn1 by dw11? dn11. So we have to now expand this, right? So I'm asking, what is this? x11. Okay, so this is dl by dn11 times x11 plus dl by dn12 times n12 times, yeah, so this one, so what is it? x21. Do you see that? Yes, no? What is that? Did I do correctly? X221, not x12. X31 and so on. Okay. So if I want to, so the claim is dl by dw is actually matrix multiplication of what and what. So let us see that. So x11, x12, x, sorry. Yes, you're right. You're right. Yeah. You're absolutely right. I said when I told first column, but when I wrote something else, right? So you're right. Good. N21, N21, N31. Okay. So same way over here. And like this. Okay. So if I arrange all the dl by dn11, dl by dn12, n21 like this. Okay, I'll arrange it like this. dl by dn n1, dl by dn12. So this, and if I want to get x11, this one, it is like multiplying by what? I will multiply. Yeah, so I will have to multiply, do matrix multiplication with. So I think I did some mistake. Yeah, so it is like matrix multiplication with this vector. x11, x12, xn1, then x21, x22, like this. Okay. So this is like x transpose. So this is like x transpose times the dl by dn. Okay. So dimensions are correct, right? So what is the dimension of x transpose? What's the dimension of x transpose? What's the dimension of x? N cross d. Correct? So this is d cross n. Okay. And what about this one? So this is n cross 2. So the output is d cross 2, which is what we have for w as well, which is d cross 2, right? W is also d cross 2. Okay. So I showed you how to do dl by dw. So we will break for coffee now. So, but point is, I have shown you how to do back propagation, right? So you get all the gradients at various steps, then you do eta times that gradient and you repeat till convergence. So that is the whole idea. This is, I have shown you only for a single layer linear regression type model. But if there were multiple such layers, you can repeat this procedure. Okay. And the goal is you can, whenever you have a neural network, you can implement it as a, so this is what all these standard packages do, right? So when you create neural networks, you will tell how many neurons, what is the activation function, what is the loss function, like that you will tell multiple such layers and it will do the operations. Okay, but that's just because it's a class. So it maintains a list of operations. So operation 1, operation 2 and operation n. So when you do forward pass, you will pass it through the op1 dot forward, right? And that output you will give it to op2 dot forward of op1, like that. You see what I'm saying? So you just chain them together, and when you do reverse, you will do the opposite thing, and that way you get the gradient and you do eta times that and you continue till convergence. So that is the whole back like back propagation. Okay, so this same idea if time permitted, we could have done something else as well. But for now, I think if you can implement this in this spirit for at least 2 layers, that means that you will have understood this well enough. So during your lab, I will be around, so we'll try to implement this. Okay. All right. So we'll break for coffee. If you have any questions, you can come back and ask. All right. So we'll break for coffee. Yeah.
Oh, maybe I should take this for the online people. Okay. So I have circulated a form on the Discord. You should you need to fill in the form. In order to, oh, sorry, I should not take this in front of near the phone apparently. In that form, you need to fill in the email, the name, the email will be captured, the name, the session number, the day and the session number, and you have to give in a code, right? And this is a feeble attempt at making sure people are not doing it from home. So each session will put up a code out here, and this session's code happens to be UHWPK. Let me just write it out here. UHWPK. I mean, of course, as I said, this is a very feeble attempt. All caps. And that's it, right? So the same, and the form will remain the same. You just select the day and the session. The only thing that we will change in each session is that we'll put up this code up here. That's all. Yeah. Huh? First letter is U. My handwriting is terrible. Yes. Okay. That's all. So let's have chai, coffee. Thank you.